Not long ago, it seemed that the environment was going to get a lot worse before it got better. At first, things did get worse. In the year 2007, the process of urban growth consumed great amounts of energy and raw material and produced large quantities of untreated waste and harmful gas. Nations, companies, and cities all announced bold sustainability plans to alter the process. But these good intentions had limited results. Then something happened that altered our way of thinking about the way cities function. Research and development accelerated the rate of clean energy production to the point that it began to approximate Moore's law. Moore's law was the tech boom observation that the number of transistors on a chip doubles every 24 months, resulting in the doubling of a computer's processing power. This decade-long period of exponential development set the stage for a renaissance of new inventions in technologies, applications, and products in the IT field. When Moore's law met sustainability, advances in sustainable building technologies led to an increase in the production of wind and solar energy. As a result, the net energy demand of buildings started to decline. Around this time, the term urbanization began to take on a new meaning. It became a process of energy production rather than consumption, a mode of environmental remediation rather than a source of pollution. Urban design went from being a practice of damage control to one of wealth management. Architecture was an urgent priority for the sustainability sector. Back then, buildings used less than 30% of all electric power generated in the world, but released more than 60% of all carbon dioxide from electric uses. These attempts to improve the environmental performance of buildings led to a shortening of their lifespan. Every 24 months, wind and solar energy produced by buildings doubled. Building energy consumption decreased by 50%. A building's life was determined by ever more demanding requirements to produce greater amounts of energy and to reduce energy consumption. Because a new building could generate 64 times more energy than a 10-year-old building, it became imperative to replace older, inefficient buildings for the sake of the overall environment. At the scale of the city, this process had compounding benefits. The continual introduction of newer, more advanced buildings created an unprecedented urban situation. Cities began to accumulate a surplus of energy. Busan, Korea's second-largest city, was particularly aware of the delicate coexistence of commerce and the environment. Busan is highly industrialized. It has the country's major commercial port. At the same time, its natural features, like its beaches and lush shoreline, make it a major tourist destination in Asia. Environmentalism was Busan's ticket. The city needed to preserve its natural features, while at the same time supporting development. Busan was one of the first cities to apply sustainability technologies in the era of Moore's law. Even as early as the 1990s and 2000s, the lifespan of commercial buildings were already shorter than the functional life of their materials. In districts like Hyundai Beach and Yangjae, the newest buildings were typically the first to be destroyed and replaced as part of an ever faster cycle of real estate speculation. This cycle would later have benefits for the environment. Busan began to encourage the replacement of older buildings with newer ones, having improved sustainability technologies in order to reduce energy costs. To achieve even greater environmental benefits, new buildings were clustered closer together. This provided the city with increased open space, which the people of Busan referred to as Moore space, in reference to the observer of Moore's law himself. From a sustainability perspective, the ideal urban formula is high population density and minimal building footprint. High urban density reduces the energy consumption and carbon output from ground transportation. An urban footprint of minimal area diminishes the heat sink effect, allowing heat to rise naturally and reduce energy needs for cooling buildings. The primary limitation of solar and wind systems is to store energy for future use. To store the energy and to ensure its future availability, architects in Busan employed a hydrogen conversion system. This is how a hydrogen conversion system works. Wind and sun rays are collected to generate electricity. When water is introduced to electricity through a process called electrolysis, hydrogen is produced. The hydrogen is then pressurized and stored. When energy is needed, the stored hydrogen is introduced into a fuel cell, which converts the hydrogen back into electricity. Today, in the year 2025, our buildings in Korea typically have photovoltaic panels on their exterior to collect solar energy. Wind is typically collected through a double-layer building envelope that rotates to capture the wind. The energy is converted into hydrogen and then stored inside the building envelopes, which are made of ETFE, an extremely lightweight polymer that allows daylight to pass through. As energy is needed, the hydrogen is converted into electricity. A similar layer of ETFE pillows, filled with helium, insulates the stored hydrogen. Together, the hydrogen and helium create uplift, elevating the building from the ground. For the most part, our buildings float in the air. They are assembled in mixed-use clusters of commercial and residential structures ranging in area from 2,000 to 80,000 square meters. The clusters are tethered to the ground by strands that function as service and circulation cores. To decrease the energy consumption of buildings on the ground, the clusters expand and contract. In summertime, they expand outward to increase ground shade coverage. During the summer, increased sun exposure produces more hydrogen. The increase in hydrogen lifts the buildings to higher altitudes. At higher altitudes, the air temperature is cooler, which in turn reduces the energy loads for internal cooling. The building clusters move over the course of a day. For example, in summertime, during the morning hours, the commercial buildings array further apart to increase their exposure to sun and wind. This generates more power, which is used to accommodate the rise in peak energy demand during working hours. In wintertime, as night falls, the commercial buildings move closer together to store heat gained over the course of the day. As energy production increases, carbon dioxide emissions decrease. The use of clean energy processes like the hydrogen system has helped to reduce the amount of carbon dioxide emitted from building uses. The surplus of clean energy has offset the need for fossil fuels. As a result, the overall amount of carbon dioxide emissions has further declined. Now that sustainability technology advances, our urban condition improves. As you can see, in cities such as ours, the beaches are clean. Our older business and residential districts have ample green areas. For now, parts of our city float in the air. Living in these buildings has become a normal way of life. These buildings have become as iconic to our city as our previous infrastructure and urban projects. But we have also come to realize that these structures will soon pass. As technologies advance, they too will be replaced by newer, more environmentally sustainable structures. The experience of the last 2 decades has allowed us to realize that advances in sustainability technology have provided an opportunity to rethink the process of urbanization. It has given unforeseen power to architects to define a new type of city by learning from environmental imperatives.